One, disfluencies. These are natural speech imperfections. Don't overuse them, especially for experts, but sprinkle them in realistically. Fillers. Um, no fear. Use sparingly, perhaps more at the start of a turn or when searching for a word. Example, host speaker. So today we're diving into GeoAI. Verbal pauses connectors, like, sort of, kind of, I mean. These softened statements or bridge thoughts. Example, expert speaker. Yeah, it's, kind of the intersection of geography and AI. Host speaker, right? Like equipping computers with a geographical sense. Repetitions, repeating small words or starting phrases. Example, expert speaker. And the need for understanding big data is huge. False starts for formulations. Starting a thought, stopping and rephrasing. Example, host speaker. Okay, so what part are we? What specific area are we focusing on? To interruptions and overlapping dialogue. Speakers often briefly talk over each other or jump in with short agreements or questions. The alternating line structure inherently supports this for TTS. Example, host speaker, which sounds incredibly complex. Expert speaker. It can be, yeah, but the power. Host speaker. Right. Expert speaker, not the power it offers, is significant. 3, back-channeling feedback. Short utterances showing the listener is engaged. Examples. Okay.
Yeah.
Yeah, I see. Gotcha. Sure. Example. Expert speaker. Using these deep learning models. Host speaker. Expert speaker. And that allows for much greater accuracy. Host speaker. Okay. 4, contractions. Use standard contractions extensively. Examples. It's don't, can't, were, that's, isn't, aren't, you'll, will. Example, host speaker. That's a great point. We're going to explore that. 5, informal language and colloquialisms. Use natural, everyday language appropriate for a conversational podcast, avoiding overly academic or stilted phrasing. Examples, digging into, big deal, get into, stuff like that. Basically, pretty much figure out, kick things off. Example, host speaker. So, what's the big deal with GeoAI? What can it actually do? 6, shorter sentences and fragments. Break down complex ideas into shorter sentences or even sentence fragments for easier listening and more conversational pace. Example, expert speaker. We looked at different data types: remote sensing, street view, geoscientific data. Each needed a slightly different approach, 7, tag questions. Occasionally turn statements into questions to engage the listener or seek confirmation. Examples, right? Anthel belt, isn't it? Example, host speaker. It automates a lot of the tedious work, right? 8, direct address. Use you to speak directly to the listener. Example, expert speaker. So what you'll find is that these models learn patterns. 9, transition markers. Use natural transition words and phrases. Examples. So, all right, okay, now moving on. Well, anyway, example, host speaker. Okay, so we've talked about the models. Now, how are they actually used? 10, varying pace. Mix slightly faster explanations with pauses or slower segments for emphasis or when explaining complex points. This is more for the TTS engine's delivery, but the script structure can guide it. 11, enthusiasm and engagement. The language should reflect the speaker's interest in the topic, guided by word choice and sentence structure. Example, host speaker. Wow, that's fascinating. So you can actually...
Welcome to the deep dive. Today, we're venturing into a really dynamic field where geography meets artificial intelligence. We call it GeoAI. Think of it as equipping computers with a geographical intuition, allowing them to analyze our world in incredibly powerful new ways.
Exactly. GeoAI, or geospatial artificial intelligence, it's right at the frontier of spatial analytics within geography.
Okay.
And it's a timely development, really. The remarkable progress in deep learning, the sheer computational power now available, and the pressing need to make sense of vast amounts of data have pushed AI into diverse fields.
Yeah.
I mean, from understanding molecular interactions in chemistry to solving complex mathematical problems and even transforming medical science, it's everywhere.
Okay, GeoAI sounds like a huge topic. What specific area are we really digging into today?
Well, our focus is mostly on how GeoAI is being applied to large-scale image analysis.
Image analysis, right?
Yeah. We're going to explore the fundamental methods behind this research, the exciting progress in geospatial applications, and crucially, how it's offering advantages over more traditional methods.
Okay.
Our aim is basically to give you a clear understanding of this rapidly evolving field without getting, too bogged down in excessive technical detail.
Makes sense. So what kind of information are we talking about here? What's the raw material for this GeoAI analysis?
We'll be looking at a variety of image and structured data. So imagine satellite and drone images giving us that valuable overhead perspective. Street view images providing that critical human viewpoint, and then various forms of geoscientific data. We'll discuss how AI is used to analyze these different types of data for a whole range of image analysis and machine vision tasks.
Got it. So what's the big deal with GeoAI? I mean, what can it do that older methods maybe couldn't?
It's a great question. Our review of the research highlights 6 key strengths, really.
Okay.
First, GeoAI enables us to perform analytics on a much, much larger scale than ever before.
Right. Big data.
Exactly.
Yeah.
Second, it automates processes, particularly in identifying and extracting features from data. That's huge.
Yeah, less manual work.
Third, we're seeing significantly improved accuracy in many analyses and predictions. Fourth, GeoAI is proving remarkably sensitive to detecting even subtle changes in our environment.
Interesting.
Fifth, it's surprisingly robust when dealing with noisy or imperfect data, which is pretty common in real-world observations.
Definitely.
And finally, the field is just advancing very, very rapidly, with new techniques and applications appearing all the time.
Those sound like major leaps forward. Now, you mentioned that GeoAI development has gone through different phases. What are those?
Yes, it's helpful to think of it in maybe 3 stages. The initial phase was pretty much just introducing existing AI methods into geography, basically testing if they could work together.
Kind of exploratory.
Right. The second phase, which is where a lot of the current work lies, involves adapting AI. This means recognizing the specific challenges posed by geospatial problems, and then modifying and enhancing AI methodologies to address them, tailoring them, essentially.
Makes sense.
The third and perhaps most impactful phase is when insights and techniques developed within GeoAI are then applied back to computer science and other fields.
Oh, interesting. So it's a two-way street.
Exactly. This involves incorporating spatial principles, like, the idea that things near each other are often more related into new AI models. This could potentially lead to more powerful AI that can be used across many disciplines.
Wow.
Our discussion today will really focus on those second or third phases, as they represent GeoAI's unique contributions.
So the goal of this deep dive is to really grasp the key AI techniques in play and how they're being applied to geospatial data. What specific types of data are we focusing on then?
We're prioritizing cutting-edge work in AI and deep learning, as well as those sort of foundational studies that first brought AI into the geospatial domain.
Okay.
So we'll be looking closely at applications using remote sensing images, that's your satellite and aerial data, street view images, and various forms of geoscientific data. Now, while topographic mapping is certainly important and a major governmental focus, it won't be our main subject today. A lot of that ground's been covered elsewhere.
Understood. And how did you even begin to, look at all this research? It sounds like a massive field.
Yeah, it is. We organize the research primarily by the type of geospatial data being used.
Okay.
So we have sections focusing on remote sensing, street view, and geoscientific data. For each of these, our approach to reviewing the literature differed slightly based on how long we've been collecting that type of data and how readily available it is.
Right, different histories there.
Exactly. For remote sensing, which has a longer history, we looked at it through the lens of different tasks like identifying objects in images or segmenting images into different land cover types, and compared how traditional methods performed against these newer GeoAI and deep learning approaches.
Okay, comparison is key.
Yeah. For street view, which is more recent, we organized our review more by application, such as how it's used to understand neighborhood characteristics.
Gotcha.
And for geoscientific data, we again focused on specific applications and compared traditional and GeoAI methods.
That's a logical way to break it down. Now let's talk about the core tools. What are the key AI techniques that underpin GeoAI?
Right. At the heart of GeoAI's methods, we'll be discussing several important AI techniques. These include feed-forward neural networks, which are a fundamental building block in many AI systems.
Okay.
Then we have convolutional neural networks, or CNNs.
Heard a lot about those.
Yeah, they've become incredibly powerful for handling spatial data, especially image analysis. We'll also cover recurrent neural networks, or RNNs, and their more advanced version, long short-term memory networks, or LSTMs.
Right, for sequences.
Exactly. They're designed to process sequences of data, like time series. And finally, we'll touch on transformer models, which have really, really revolutionized the field of AI in recent years.
Yeah, they're everywhere now.
They are. These models are now dominant in many areas of modern AI research.
Okay, let's dive a bit deeper into some of these models. You mentioned CNNs quite a bit. What's the basic idea behind them?
Yeah, absolutely.
Yeah.
Let's maybe start with the fully connected neural network, or FCN. Think of it as a sort of basic component often used in more complex deep learning structures.
Okay, foundational.
Right. Then we have the convolutional neural network, or CNN. Its architecture is specifically designed for understanding images. It uses layers called convolution layers. Think of them like specialized filters that learn to detect patterns in the image,
Uh-huh.
followed by max pooling layers that help the model become more flexible and less sensitive to small shifts or changes in the input.
Okay.
You often see labels on these internal feature maps like 8 at 64 by 64. The 8 tells you how many of these learned filters are being applied, and 64 by 64 indicates the size of the resulting filtered image.
I see.
Essentially, the CNN learns to see the image through different lenses, each highlighting a specific pattern. And this ability to automatically learn relevant features directly from the image is a key advantage. No need to handcraft them.
Right. That seems powerful. And what about RNNs and LSTMs? How do they deal with data that changes over time?
Good question. Recurrent neural networks, RNNs, are designed to process sequential data. The key idea is that they have a kind of internal memory that gets updated as they see each new piece of data in the sequence.
Like a running tally.
Sorta, yeah. They also reuse the same learning rules at each step in the sequence, allowing them to recognize patterns that unfold over time.
Okay.
Now, LSTMs, or long short-term memory networks, are a more sophisticated type of RNN. They're much better at remembering information over longer sequences.
Ah, hence the name.
Exactly. Imagine an LSTM having not just short-term memory, but also a kind of longer-term storage. It achieves this through a more complex internal structure. It includes a forget gate, which decides what old information to discard, and a cell state that acts as this long-term memory.
Wow, complex?
It is. The hidden state in an LSTM can be thought of as the output feature the model produces after processing the sequence up to a certain point, and it takes an input feature vector that evolves as the sequence progresses. So while a regular RNN might struggle to remember something from way back at the beginning of a long sequence, an LSTM is much better equipped for this.
Interesting. And finally, these transformer models that are causing such a stir.
Yes, the transformer architecture. It's quite a departure from previous sequence processing models like RNNs. It's based on an encoder and a decoder, and is designed for sequence-to-sequence learning, basically, transforming one sequence into another, like translation.
Okay.
Unlike RNNs, transformers don't process the input step by step. Instead, they can look at the entire input all at once.
How does that work?
The core of this is the attention mechanism. When you feed in a sequence, say a sentence, the self-attention part calculates how much each word in the sentence relates to every other word.
Okay.
It's like the model is asking itself, when I think about this word, which other words in this sentence should I pay the most attention to? It then uses these relationships to create a really rich representation of each word. That's the encoding process.
I see.
Before this even happens, the words are converted into numerical form through input embedding. And something called positional encoding is added to tell the model the order of the words, since it's not processing them sequentially.
Right. It needs to know the order somehow.
Precisely. The encoder then typically has feed-forward layers to further refine these representations. The decoder has a similar structure, but includes masked attention.
Masked attention.
Yeah, because the decoder is often used to predict the next element in a sequence, like the next word in a translation. The masked attention mechanism only allows it to look at the elements that have come before the current one. Can't cheat by looking ahead.
Ah, makes sense.
The decoder also has a cross-attention module that uses both the encoded input and the already generated output to figure out what should come next. This allows it to generate a sequence, like a translated sentence, based on the input. It's very powerful.
Fascinating stuff. So with these powerful AI tools, how are they being used to analyze remote sensing images? What are the big differences compared to how it was done before?
Well, in traditional remote sensing image analysis, we often relied on techniques like edge detection or manually designed features, things like SIFT, HOG, BOW, you might have heard of them.
Vaguely, yeah.
These methods usually require a lot of expert knowledge about the specific application, and frankly, it might not work well in different situations. They're not very adaptable.
Right.
Now, CNNs have become incredibly powerful at automatically learning these features. Their main advantage is that they can learn relevant patterns directly from the raw imagery with very little or no pre-existing knowledge.
That's the key, learning from the data itself.
Exactly. But while CNNs have been hugely successful in areas like identifying objects and segmenting natural scene images, applying them to remote sensing data brings its own set of challenges.
Like what?
For instance, we're often looking at objects from directly above, right? The nadir view. The overall scene is vast, but the objects themselves might be quite small.
Okay.
This limited visual information, along with issues like changes in orientation, things look different when rotated scale variations, complex backgrounds, and things being partially obscured by clouds or shadows.
Yeah, lots to deal with.
It often means we need to adapt and enhance these deep learning models specifically for remote sensing. It's not just plug and play.
Right, those are some unique challenges that come with the overhead view. Let's get into some specific uses. How is GeoAI changing how we classify entire remote sensing images? Like saying this is a forest, this is a city.
Right. Image-level classification here means predicting the overall content of a remote sensing image with one or more labels, sometimes called multi-label classification. It's used for things like identifying the type of land use or land cover in an area, or classifying images based on the natural or man-made features they contain. In computer vision generally, CNNs have become the go-to method for this. Large datasets like ImageNet really help drive progress. Over the past few years, we've seen continuous improvements in CNN models specifically for remote sensing imagery. Key developments like AlexNet, which showed the power of letting the network learn features automatically. VGG, which demonstrated the benefits of using really deep networks.
Deeper is better sometimes?
Sometimes, yeah.
Okay.
Inception, which can look for features at different scales within the image simultaneously. And ResNet, which introduced a clever way to train even deeper networks effectively. They've all been very influential.
Okay.
A particularly useful technique is transfer learning.
How does that work?
Think of it like this. A model is first trained on a massive dataset like ImageNet to learn general image features like edges, textures, basic shapes.
Right, general visual knowledge.
Exactly. And then its knowledge is fine-tuned for specific remote sensing tasks, like identifying different crop types or types of buildings.
Yeah.
This can save a lot of training time and often improve accuracy, especially when you don't have tons of labeled remote sensing data.
That's smart.
Yeah. And interestingly, researchers are also exploring combining CNNs with graph neural networks, or GNNs.
GNNs, how do they fit in?
GNNs are good at understanding relationships between different entities. So they can help capture the spatial connections between different features or objects within a remote sensing image, potentially leading to even better classification, like understanding that a road is usually next to buildings in a city.
Adding context.
Precisely.
Yeah.
Studies comparing different models have even shown that CNN architectures inspired by Inception tend to perform very well on land use datasets like UC Merced. And sometimes, maybe surprisingly, CNNs can even outperform GNNs on the same data, depending on the specific task.
That's really interesting how different AI approaches can be combined or compared. What about when we need to get down to the pixel level? How is GeoAI impacting semantic segmentation in remote sensing?
Right, semantic segmentation takes image analysis to a much finer level. Instead of classifying the entire image with one label, it involves classifying every single pixel in the image into a specific category.
Wow, every pixel.
Every pixel. Essentially dividing the whole image into meaningful regions that represent different objects or types of land cover, roads, buildings, water, trees, different crop types, etc.
Okay, that sounds much more detailed.
It is. Traditionally, methods like looking at groups of pixels with similar characteristics, identifying boundaries between different regions, or using clustering algorithms were used. But neural network-based models have really transformed this field.
How so?
These models learn a direct mapping from the input image pixels to the output classes. It's different from image-level classification, where you go from an image to a single label. Here it's image to image, pixel by pixel.
Gotcha. More complex.
Definitely. Because of this detailed pixel-level analysis, it's a more complex and computationally demanding task. Most of the successful neural network models use an encoder-decoder architecture.
Encoder-decoder, like we discussed with transformers.
A similar concept, yeah. Think of the encoder as shrinking the image down while extracting important features at different scales, and the decoder as then building back up a segmentation map where each pixel is assigned a class. Models like UNet, FCN-SegNet, and DeepLob are common examples you might hear about.
Okay. And where is this useful?
Oh, incredibly valuable in geospatial research for precisely identifying areas of interest within an image. Consider precision agriculture, where you need to accurately separate crops from weeds for targeted spraying.
Right, very practical.
Or land use and land cover analysis for monitoring urbanization or deforestation with high detail. It's also being used for practical applications like automatically removing clouds and shadows from imagery.
That's a huge problem in satellite images.
It really is. And for extracting road networks and even estimating the width of roads, there's also ongoing work to make these techniques faster for real-time processing, to effectively use data from different parts of the electromagnetic spectrum, not just visible light, and to improve the detection of very small objects, which can be tricky.
Going from a 2D image to understanding 3D structure seems like a big leap. How is GeoAI helping with estimating the height or depth of objects from 2D remote sensing images?
Yeah, that is a big challenge. Understanding the three-dimensional geometry of objects in remote sensing imagery is really important for many applications. Things like creating detailed 3D models of cities, aiding in urban planning, even in fields like ocean engineering.
Right, 3D context matters.
It does. Now, while specialized data like LiDAR, shooting lasers down and measuring the return and its resulting digital surface models, DSMs, can provide this heightened depth information very accurately, they can be expensive to acquire and might not be available everywhere.
Sure.
Remote sensing imagery, on the other hand, is often more readily available globally and more cost-effective.
So how do you get 3D from 2D?
In computer vision, there are two main approaches. One is monocular estimation, trying to infer depth from a single image.
From just one picture? How?
It often uses probabilistic graphical models. Think of a system that considers different possibilities and assigns probabilities based on context clues and what it knows about the world to relate image features to a height or depth value. These features could be manually identified based on semantic labels or even extracted by CNNs.
Okay. And the other way?
The other is stereo matching, which uses two images taken from slightly different viewpoints, like our own eyes.
Ah, like stereo vision.
Exactly. It works by finding corresponding points in the two images and then using the slight difference of their position, the parallax, to calculate the depth through triangulation.
Okay. But applying this to overhead remote sensing images sounds tricky.
It presents some unique hurdles, yeah.
Yeah.
The images are often taken from directly above, so they lack some of the perspective cues we see in everyday photographs. They might also have limited visual context or resolution, and the objects we're interested in might be quite small.
Right. So what are the GeoAI solutions?
Researchers have developed techniques like using joint loss functions in CNNs. That means the network is trained to do two things at once: semantic labeling, what is this pixel, and regression, how high is this pixel. This helps utilize the pixel-level information better.
Interesting multitask learning.
Kind of, yeah.
Hmm.
Convolutional neural networks, trained using existing DSM data as a guide or supervision, have also been used to sort of learn how to estimate height, reducing the need for extensive manual labeling.
Okay.
And for particularly difficult areas like water bodies, where it's hard to find matching points because water surfaces lack distinct features and reflect light. Weirdly, newer approaches like semi-global block matching are being explored.
Image quality is always a concern, isn't it? How is GeoAI contributing to enhancing the resolution of remote sensing images? This idea of super resolution.
Exactly. High-resolution images are always more useful, but aren't always available, especially when covering large areas, often due to sensor limitations or cost.
Right, you can't always get the sharpest picture everywhere.
Precisely. That's where super resolution comes in the process of reconstructing a higher resolution image from one or more lower resolution images, basically making a blurry image sharper using AI.
How is that done traditionally?
Traditionally, methods included simply interpolating pixel values, guessing the values in between existing pixels.
Like by cubic interpolation?
Yeah, things like that. Also using statistical models that learn the relationship between low and high resolution image patches, applying probability models, or even transforming the images into a different mathematical space, like the frequency domain using Fourier or wavelet transforms.
Okay, sounds complex.
It could be. But deep learning has significantly advanced super resolution. CNN-based methods learn a direct mapping between low and high-resolution image pairs using convolutional layers. Think of it as the network learning how to intelligently fill in the missing details.
Learning to sharpen the image.
Pretty much. There are many different variations of these CNN-based solutions that differ in their network structure and how they are trained. Generative adversarial networks, or GANs, have also been used. They address the issue that some simpler CNN reconstructions can look a bit too smooth or blurry.
How do GANs help?
GANs use a generator network to create the high-resolution image and a separate discriminator network that tries to judge how realistic it looks compared to real high-resolution images. This competition pushes the generator to create more photorealistic results.
Clever?
Yeah. Beyond just regular images, there's also a lot of research on improving the resolution of hyperspectral images, which contain much more detailed spectral information across many bands.
Right, more than just red, green, blue.
Exactly, often by combining them with higher resolution panchromatic or black and white images. And more recently, innovative approaches like models based on efficient net and something called unsupervised deep gradient networks are even pushing the boundaries. allowing for significant increases in resolution potentially, without needing perfectly paired low and high-res examples for training.
Tracking moving objects from space or air must be incredibly challenging. How is GeoAI helping with object tracking in remote sensing imagery?
It is indeed a very complex task. Object tracking involves estimating the position and maybe the size or shape of a specific object like a vehicle, a ship, or even an iceberg as it moves through a scene over a sequence of images.
Right.
It has applications in things like monitoring vehicle traffic, maritime surveillance, tracking wildlife, video indexing, even human-computer interaction in some contexts.
What's the general process?
Usually involves first detecting the object in the initial frame, then identifying some unique visual characteristic or feature to follow, and finally using a tracking algorithm to predict its movement and find it in subsequent frames.
Okay. But the remote sensing challenges must make this harder.
Definitely. We face extra difficulties, like the object appearing very small, potentially significant changes in its orientation or appearance, and it being obscured by clouds, other objects, or even sensor noise.
Yeah, things can disappear and reappear.
Exactly. To deal with the low resolution, techniques like optical flow-based trackers, which analyze how patterns of brightness move in an image over time, have been used, sometimes combined with color information if available.
And deep learning.
Deep learning techniques, particularly CNNs, are showing great promise. They can be trained with carefully selected examples of what the object looks like and what other things look like, negative samples, to learn a robust appearance model.
Okay.
These models can even incorporate things like saliency modules to help them focus on the most important parts of the image related to the object, and use techniques like local weight allocation to improve their efficiency and focus.
And what about rotation, if a ship turns?
Good point. For handling changes in orientation, specialized methods like rotation adaptive correlation filters, RACF, have been developed. They try to explicitly estimate how the object is rotating and adjust the tracking filter accordingly.
Change is constant, especially on our planet, right? How is GeoAI being used to detect and understand changes in land surface conditions using multiple remote sensing images taken over time?
Precisely. Identifying changes in land surface conditions over time using multiple remote sensing images, we call this multi-temporal analysis, is crucial for monitoring things like deforestation, the expansion of cities, urban sprawl, the impact of natural disasters like floods or fires, agricultural monitoring, tracking glacier melt. The list goes on.
Super important applications. How is this done before AI?
Traditionally, methods included things like simply subtracting the values of corresponding pixels in two images taken at different times.
Image differencing.
Right, or calculating ratios between different spectral bands, analyzing how the spectral signature of an area changes over time, change vector analysis, and using statistical techniques like principal component analysis to highlight areas of change.
Okay, mathematical approaches.
Mostly. But deep learning is offering new and arguably more powerful ways to approach this. Approaches using CNNs, recurrent neural networks, since we're dealing with time sequencing,
RNNs make sense here.
and Siamese networks, which are specifically designed to compare two inputs, like image patches from different dates to see how similar or different they are focusing on learning not just the spectral characteristics of change, but also the spatial patterns and how these patterns evolve over time.
So understanding the context of the change.
Exactly. By being able to analyze sequences of images and understand the temporal relationships between features, these deep learning methods are proving very effective at pinpointing and characterizing changes in our environment, often with improved accuracy compared to traditional methods.
Finally, in the remote sensing realm, looking towards the future, how is GeoAI being applied to forecasting or predicting future conditions using this data?
Yeah, forecasting, predicting future observations based on past and present data is essential in so many fields. Predicting weather patterns, anticipating droughts, changes in land use, crop yields, even things like retail sales rely on it.
Right.
Historically, this relied heavily on statistical models applied to historical data. Remote sensing provides this incredible wealth of long-term, large-area observations that can be fed into these models. Often, people use derived measures or indices calculated from the satellite data, like NDVI for vegetation health, LST for land surface temperature, or drought indices like VTCI.
Using indicators from the satellite data.
Right. More recently, deep learning techniques are being explored specifically for time sequence forecasting using remote sensing data. Models like deep belief networks, an older deep learning model, and especially LSTMs, given their strength with sequences, have been used for tasks like short-term drought prediction and longer-term rainfall forecasts. We're even seeing direct use of sequences of remote sensing imagery to predict things like the changes in the surface area of lakes over time or future vegetation conditions.
Interesting.
And excitingly, transformer models, which we discussed earlier for sequence processing in general, are also proving to be very powerful tools for time series forecasting with geospatial data. They can potentially capture longer-range dependencies in time, allowing us to make more accurate predictions about our dynamic planet.
That's a really comprehensive overview of how GeoAI is transforming remote sensing. Fantastic. Now, let's switch our focus to another fascinating source of geospatial information, street view images. How is GeoAI leveraging this ground-level perspective?
Right. Street view images offer a really unique human-centered perspective of our surroundings. It's the view from the ground.
Yeah, totally different from the satellite view.
Completely. And with the increasing availability of this detailed image data from companies like Google, Baidu, Mapillary, etc., GeoAI is being used in a wide range of innovative ways.
Like what?
Think about automatically assessing the characteristics of neighborhoods, calculating how much of the sky is visible from street level, the sky view factor we mentioned, detecting changes in urban areas over time, understanding how people perceive different places, identifying what makes certain locations visually unique, and even predicting human activities.
Wow. That's a lot you can get from those pictures.
It is. Traditionally, getting this kind of information would require really time-consuming in-person surveys or sending people out for on-site inspections. Very expensive, very slow.
Right.
But street view imagery, combined with the analytical power of GeoAI and deep learning, allows for large-scale automated extraction of valuable urban information.
So what kind of neighborhood characteristics are we now able to automatically assess using GeoAI and street view images? Can you give some examples?
We can learn quite a lot, actually. Researchers have used this data to infer various social and environmental properties. For example, studies have estimated demographic information or socioeconomic status based on the types and distribution of vehicles parked in neighborhoods.
You can tell that from the cars.
Apparently, yeah, using sophisticated models like deformable part models and CNNs to identify car models and correlate them with census data. House prices have also been predicted by training CNNs on images of properties and their surroundings, combined with statistical models to account for location and other factors.
Okay. What else?
The amount and quality of green spaces in urban areas like trees, grass are being assessed, using deep learning segmentation techniques that can identify vegetation in the street view images.
Measuring urban greenness from the street.
Exactly. And even factors related to how walkable a neighborhood is, things we intuitively sense are being calculated using CNN-based indices. These analyze street-level visual cues like the presence and condition of sidewalks, pedestrian crossings, street furniture, building setbacks, etc.
That's incredible detail. You mentioned calculating sky view factors. Why is that important, and how is GeoAI helping there?
The sky view factor, or SVF, is basically a measure of how much of the sky is visible from a particular point on the ground looking up. It's a really important factor in understanding urban climate, especially the urban heat island effect.
How so?
Tall buildings and narrow streets trap heat and block the sky, reducing radiative cooling at night. So areas with low SPF tend to be hotter. It affects thermal comfort, energy use, air pollution dispersion.
Okay, so it's a key urban climate variable.
Definitely. Traditionally, calculating SVFs involved maybe using fisheye lens photos or creating synthesized hemispherical views from 3D city models, and then using computer vision techniques like edge detection to identify the sky area.
Sounds tedious.
Could be. But GeoAI, using powerful segmentation networks like PSPNet, allows us to automatically identify and separate the sky, trees, and buildings in street view images, and then calculate these view factors much more efficiently across large areas.
Automating the process.
Exactly. There's even research exploring the correlation between sky view factors calculated this way and the actual surface temperatures observed in urban environments using thermal sensors.
Detecting changes over time is crucial for understanding urban dynamics. How is GeoAI being applied to detect neighborhood changes using street view imagery?
Yes, cities are constantly changing. By analyzing street view images taken at different times, Google Street View often has historical imagery, for example.
Right. You can go back in time.
We can now automatically identify changes in the physical environment of neighborhoods. For example, CNNs are being used to detect alterations in building facades over time. renovations, new constructions, demolitions, providing valuable data for urban planners and researchers monitoring urban development.
Okay.
There's also work combining street-level images with satellite data, like those from the Sentinel program, to monitor changes in things like grassland cover or tree canopy in urban and peri-urban areas over time. Gives us a more comprehensive picture by fusing ground and aerial views.
Understanding how people perceive places is fascinating. How is GeoAI helping us gain insights into human perceptions using Street View data? This feels more subjective.
It is more subjective, but that's what makes it interesting. This is a really exciting area. Researchers are using GeoAI to try and quantify the relationship between how people feel about environments, safety, beauty, liveliness, and the visual characteristics of those environments.
How do they measure feelings?
Well, one approach involved extracting human emotions from faces detected in publicly available photos from sites like Flickr, and then linking those detected emotions, happiness, sadness, etc., to the visual features of the locations where the photos were taken, using spatial clustering.
Using social media data.
Right. More directly using Street View images, advanced CNNs trained on large datasets of labeled images, like the MIT Places Pulse dataset.
What's that?
Places Pulse collected thousands of images from Google Street View and had people rate them based on perceptions like safe, lively, boring, beautiful. So researchers can train models on this data.
Connecting images to human judgments.
Exactly. And then use these trained models to predict how people might perceive new urban areas based solely on their visual appearance in Street View.
Wow.
By segmenting these images and analyzing the correlation between different visual elements like the presence of trees, graffiti, architectural style, building maintenance, and reported perceptions, we can gain valuable insights into urban design and its impact on well-being.
Huge implications for planners.
Absolutely. And with the increasing capabilities of edge computing, running AI in your phone or local devices, there's even potential for real-time emotion recognition, using CNNs deployed directly on smart devices, maybe analyzing a user's surroundings, though privacy is obviously a huge concern there.
Definitely. What about identifying the unique visual characteristics of different places using Street View data, making places distinct?
GeoAI is also helping us understand what makes different locations visually distinctive or unique. By applying machine learning techniques to Street View data, we can identify unique visual signatures of different places.
It's like a visual fingerprint.
Kind of, yeah. For example, CNNs have been used to classify areas with different crime rates based partly on their visual appearance, things like signs of disorder, lighting, visibility. This information can even be combined with narrative descriptions of these places, geonarratives, to provide a richer understanding of the factors that contribute to the character and perception of different environments.
And finally, can we actually predict human activities using Street View images?
Yeah.
Where people go, what they do?
Yes, that's another active area of research, often combining Street View with other data. By analyzing Street View imagery, sometimes along with data like points of interest or social media check-ins, we can start to infer patterns of human activity and even socioeconomic factors.
Examples.
For example, photos contributed by local users to platforms like Flick or Instagram, which often include street-level views, are being used to develop personalized travel recommendations based on visual preferences inferred from the images people like. And at a larger scale, researchers are using Google Street View data, analyzing the types of businesses, building density, pedestrian infrastructure visible, to estimate city-level travel patterns, or even predict local economic activity, providing valuable information for urban planning, transportation policy, and economic development.
This is all incredibly insightful. The ground-level view adds so much. Now let's turn our attention to the realm of scientific data analytics, specifically geosciences. What are some of the unique challenges and exciting applications of GeoAI in this domain?
Right. Applying deep learning in geosciences, while promising, presents some specific challenges compared to maybe standard computer vision or language processing.
Such as?
For instance, interpretability is a big one. It can be harder to understand why a complex AI model makes a particular prediction when dealing with intricate Earth systems with many interacting variables. We often need to know the why, not just the what.
Right, the black box problem.
Exactly. Ensuring physical consistency, making sure the AI's predictions don't violate known physical laws, is also crucial, but difficult to enforce. Handling the often complex, multi-scale, multivariate nature of scientific data, the limited availability sometimes of high-quality labeled data for training, especially for rare events, and the significant computational resources required for large-scale simulations or analyses are all important considerations.
Okay, so hurdles exist, but where is it being applied successfully?
Researchers are actively developing innovative solutions across a range of applications. We can talk about a few key ones.
Great. Let's start with something that directly impacts our daily lives: precipitation. How is GeoAI being used for short-term rainfall forecasting, or what's often called nowcasting?
Yeah, precipitation nowcasting, predicting rainfall intensity for the next, say, 0 to 6 hours, is really critical for public safety. Issuing timely warnings for flash floods, planning outdoor activities, managing water resources, aviation.
Super important. How is it done traditionally?
Traditionally, we've relied on two main approaches. One is numerical weather prediction, NWP models, which are based on complex mathematical equations describing atmospheric physics and dynamics. These are great for longer forecasts, but can be very computationally intensive and slow for very short-term, high-resolution predictions.
Okay.
The other approach is radar echo map-based methods. These basically take sequences of weather radar images which show existing rain and try to extrapolate their movement. Techniques that analyze the apparent motion of clouds or rain cells in these radar sequences, known as optical flow, have been common.
Tracking the rain clouds.
Pretty much. However, these optical flow methods often estimate wind motion and then extrapolate the rain intensity separately, and they might rely on predefined parameters that don't always hold true.
And deep learning's approach.
Deep learning models, particularly combinations of CNNs and RNNs, are now being trained end-to-end on vast amounts of historical radar data. The idea is to let the model learn the complex spatial-temporal correlations directly.
How do they combine CNNs and RNNs?
CNNs are great at analyzing the spatial patterns in each radar image, the shape and intensity of rain bands. RNNs, especially LSTMs, are good at capturing how these patterns evolve over time. So integrating CNNs for spatial feature extraction and RNNs LSTMs for understanding the temporal dynamics, as seen in models like Conv-LSTM and its variations.
Conv-LSTM? Convolutional LSTM?
Exactly. It basically puts convolution operations inside the LSTM cell to handle spatial data. This and similar architectures have proven very effective for improving the accuracy of short-term rainfall forecasts compared to older methods. There's also ongoing research focusing on maybe modeling the spatial structure and the temporal changes separately before combining them for the final prediction, or using attention mechanisms like in transformers.
Extreme climate events are a growing concern. How is GeoAI helping us detect and understand these events, like tropical cyclones, atmospheric rivers, or severe weather fronts?
Detecting extreme climate events is obviously crucial for effective disaster preparedness and understanding climate change impacts. Earlier methods often involve comparing weather data, temperature, pressure, wind speed against fixed thresholds defined by experts based on historical patterns.
Subjective thresholds.
Somewhat subjective, yeah, and maybe not capturing the full complexity or precursors. But deep learning allows machines to automatically learn the complex spatial and temporal characteristics that define these events by analyzing vast amounts of climate data from simulations or observations.
So learning the signature of a hurricane, for instance.
Exactly. CNNs are being used to classify image-like representations of spatial weather variables to identify these events, treating climate data like images. More advanced 3D CNN encoder-decoder models, which can process multiple weather variables over time, so 2D space plus time is the third dimension,
Right, seeing the evolution.
have shown even better performance than simpler 2D models for tasks like localizing atmospheric rivers or tropical cyclones, highlighting the importance of considering how these events develop and move.
Must be huge data sets.
Massive.
Yeah.
Dealing with the petabytes of data generated by climate monitoring and modeling requires significant computational power, and researchers are making strides in efficiently training these complex models on high-performance computing systems, often using parallel computing.
What about data quality?
That's another challenge. Training data quality, especially labels for historical events, can sometimes be an issue. So methods like semi-supervised learning, using both labeled and unlabeled data, techniques to automatically refine the labeling of events, and using reanalysis datasets which blend models and observations are being explored.
Earthquakes are another major natural hazard. How is GeoAI contributing to our ability to detect and analyze seismic events?
Detecting and locating earthquakes using data from networks of seismic stations has traditionally involved two main families of methods. One is picking-based methods, where seismologists or algorithms pick the arrival times of different types of seismic waves, the P wave and the S wave, at different stations. Then they use these arrival times to triangulate the earthquake's location and estimate its magnitude.
Okay.
The other is waveform-based methods that try to directly analyze the raw seismic signals, looking for patterns that match known earthquake signals, often using correlation techniques.
What are the downsides?
Picking-based methods can be less accurate, especially for weak signals that get lost in noise, and manual picking is time-consuming. Waveform-based methods can be very computationally demanding and might require good prior information about expected signals.
So how does deep learning help?
Deep learning is offering new approaches, particularly to the phase picking task. CNNs and hybrid CNN-RNN models, like one called PhaseNet, have demonstrated significant improvements in accurately and automatically identifying the arrival times of PNS waves, even in noisy data.
Automating the peaking.
Essentially, yes, and doing it very well. There's also work on using deep learning for the entire detection and location process, and using transformer models, like the earthquake transformer, to enhance both the detection of seismic events and the association step, figuring out which PNS wave arrivals from different stations belong to the same earthquake.
Wildfires pose a significant threat. Can GeoAI help us model and predict how they spread?
Wildfire spread modeling is a notoriously complex problem. Fire behavior depends on so many dynamic factors: wind speed and direction, fuel type, grass, shrubs, trees, fuel moisture, topography, slope, existing fire lines.
Yeah, constantly changing conditions.
Exactly. Current operational models are mostly based on physical or semi-empirical principles, incorporating these factors to simulate fire behavior. These models can be implemented using a grid-based cellular automata approach or by tracking the fire front as a vector line or polygon.
Where does AI come in?
Well, some earlier AI-based approaches, like using genetic programming, were explored for predicting the total area burned. Now, there's increasing interest in integrating machine learning, including deep learning, more deeply into the spatio-temporal prediction of fire spread. Perhaps by learning complex interactions between variables from historical fire data, or by using AI to better estimate key input parameters like fuel conditions from remote sensing, or even developing hybrid models that combine physics-based simulations with machine learning components to improve accuracy or speed. It's crucial for improving safety and resource allocation during wildfire events, but still a very active research area.
Finally, the oceans play such a vital role. How is GeoAI being used to study mesoscale ocean eddies, these large swirling currents?
Right, mesoscale ocean eddies. They're essentially large whirlpools in the ocean, ranging in size from maybe 10 to 500 kilometers across, and they can last from days to months.
Why are they important?
They're really important for transporting heat, salt, nutrients, and carbon across vast ocean basins. They basically stir the ocean. They also have a significant influence on weather patterns, cloud formation, and marine ecosystems by bringing nutrients up from the deep or trapping heat.
Okay, big players in the Earth system. How are they usually detected?
Traditionally, their detection has relied on methods that analyze physical properties derived from satellite altimetry, sea surface height, or sea surface temperature data. Methods might look for specific characteristics in parameters like the Okubo-Weiss parameter, which measures rotation versus deformation, or use wavelet analysis or filtering. There are also geometric-based methods that look for closed streamlines or circular patterns in ocean current data derived from satellites.
Where are the limitations?
These methods often have limitations. They might require setting specific thresholds that are sensitive to the region or season, or they might not work well for eddies that don't have perfectly circular shapes or are interacting with other currents.
And the GeoAI approach.
Deep learning approaches are now being explored to overcome these limitations. CNNs are being trained on satellite data to automatically learn the visual signatures of eddies. Techniques like transfer learning, using models pre-trained on natural images, are being tested. Methods for learning features from data without explicit labels, unsupervised learning, are useful since manually labeling eddies is time-consuming. There's also exciting work on developing models that incorporate known physical constraints, like conservation laws, into the deep learning architecture to ensure the detected eddies are physically plausible. The goal is to improve the accuracy and reliability of identifying and tracking these important ocean features from the huge amount of satellite data we now have.
This has been an incredibly detailed exploration into the world of GeoAI. Really fascinating stuff. To bring it all together, what would you say are the most significant strengths that we've uncovered today?
Yeah, thinking back over our conversation, GeoAI offers some really powerful advantages, doesn't it? Key among these are definitely its capacity for large-scale analysis, handling that big geospatial data.
Right.
The automation of essential processes like feature extraction, which saves so much time and effort. The generally higher levels of accuracy we're seeing it achieve in both analysis and prediction for many tasks.
Mm-hmm.
Its sensitivity, its ability to detect subtle changes in our environment that might be missed otherwise,
Mm-hmm.
its robustness, surprisingly, in handling noisy real-world data,
Yeah, that was interesting.
and just the remarkable speed at which the technology and its applications are advancing. It's moving fast.
We also touched on how GeoAI is evolving. What are your thoughts on the direction the field is heading? Where do you see it going?
Well, we're currently in this really crucial adaptation phase, as we discussed.
Yeah.
AI is being specifically tailored, tweaked, redesigned to address the unique challenges posed by geospatial data and problems. It's not just taken off-the-shelf AI anymore.
Making it spatially aware.
Exactly. But looking ahead, I believe we're moving towards an exciting export phase. That's where the knowledge gained from working with spatial data, the importance of location, distance, neighborhood scale, and the spatial reasoning principles we're developing within GeoAI will feed back and inform the design of more powerful and general-purpose AI models.
So geography influencing core AI.
I think so, yeah. These geography-inspired AI models could then be applied across a much wider range of scientific disciplines, amplifying the impact of GeoAI well beyond geography itself.
You mentioned some particularly interesting areas of emerging research towards the end there. Could you highlight those once more? The thinking locally and thinking spatially ideas.
Absolutely. We're seeing really innovative work that integrates geographically weighted learning directly into neural networks.
Geographically weighted, meaning location matters.
Precisely. It allows the models to learn relationships that actually vary depending on location, rather than assuming one rule fits everywhere. It's truly enabling AI to think locally, which is fundamental in geography.
That sounds powerful.
It is. And then there's that fascinating research tackling the challenge of limited high-quality training data, especially for image and terrain analysis. They're developing ways for models to learn useful things just from the act of counting objects in weakly labeled data.
Learning from counting.
Yeah, leveraging Toller's first law, the idea that nearby things are more related to improve object localization, even when the training labels are imprecise. It really emphasizes the need for AI to think spatially, to understand spatial context and relationships, not just patterns in the data values themselves.
So the future of GeoAI looks incredibly bright then.
It does indeed. This deepening integration between geography and artificial intelligence holds just tremendous potential, not only for solving complex geospatial problems, climate change, urbanization, resource management, disaster response, but also, as we discussed, for contributing fundamental advancements back to the broader field of AI. It promises a significant and lasting impact across numerous scientific disciplines in the years to come. It's definitely a dynamic field that's well worth continued attention and exploration for anyone interested in understanding our world